Okay, so as usual, we'll discuss first what has been done in this week, sixth week. Of course, some important going to be helpful for you. Uh, yeah. So this week studying in explain homotopic curves. We defined explicit curves where this is the explicit definition given. Uh, you might have been understanding this, but here's the clear picture on the right side of the tab. You see from gamma 0 to gamma 1, if we are able to deform continuously. So homotopy is kind of continuous deformation of curves. Okay, so if we are able to deform gamma naught continuously to gamma 1, we say gamma 1 and gamma naught are homotopic. And if in this process endpoints are fixed, so we say homotopic with fixed endpoints. So the second definition here, which is about gamma naught and gamma 1 as closed curves, are homotopic. There's not restriction like in a fixed endpoints. But here we have these two closed curves at different points. First is gamma naught there, but continuous deformation from first curve to second curve. So after this, we have given some examples. So the first example is in complex domains. If we have two curves with fixed endpoints, I mean their endpoints are same, then from one curve to other curve, there is a linear homotopy, which is defined here. And also you can see from the picture because nothing is missing in between, so we can continuously deform from one curve to other curve. So here is the definition of the homotopy, right? So after this, what we have seen is this for open set omega, if we are having homotopy between two curves, yeah, so the relation of being homotopic is equivalence relation. Gamma naught is related to gamma naught. If gamma naught is homotopic to gamma 1, then gamma 1 is homotopic to gamma naught. This kind of after this proof, some more relation about homotopy. If we have gamma naught curve, and there exists gamma 2, which says that gamma naught is homotopic to gamma 2 plus gamma 1 minus gamma 2. Okay, so of some reparametrization. Okay, so if gamma 1 and gamma 2 are two curves, such that gamma 2 is reparameterization of first curve, so they are also homotopic, right? Are you able to see them? Because they represent same curve, but speeds are different, right? Reparameterization is kind of either speed is different or parameter interval is different, but they are same curve. So constant type homotopy will give us, or if his speed is different for both curves, but they are at the same place, we can change our homotopy because H is mapped from 0 1 cross AB to omega. So maybe in the definition we can change where H depending on gamma. For example, in at gamma, right? I am unable to write here, right? I hope now I can write. So somehow we can change these things in inside interval t. In place of t, we can place uh, parameterization. Parameterization is given by a non-decreasing function. So t can be replaced by that function. Means phi of t. So homotopy. Right. So after this, yeah. So we are here. The third part is that uh, gamma naught minus of gamma naught. If you add them, you get constant curve, or gamma one is equal to z naught every time. So this is homotopic to constant. So here we have some exercise. Gamma naught is homotopic to gamma naught tilde. Gamma one is homotopic to gamma one tilde. Then gamma one plus gamma naught plus gamma one is homotopic to the sum of the other two curves. So pictures you can see something like this. If let's say, okay, what is right. Let me use red color so that, so I'm writing on the left. If z naught is this is z1, and here is our gamma 1, sorry, gamma naught. Another one, gamma 1, let's say here is gamma 1, and gamma naught is homotopic to gamma naught tilde. So there exists deformation from this curve to the gamma naught tilde, and here also gamma 1 tilde you have deformation from gamma naught. Now if you take concatenation of these two curves, uh, this is the second curve. First curve is this concatenation, and right. So what we do in the notation, if you want to define explicit homotopy, in this place, let's say h naught, and in this homotopy you have, let's say, h1. Then what you can do, you can concatenate them, right? So you have to define h depending on this s naught and h1, and that is, I think, you can do this explicitly, just like this. Why is this not writing? So my pen is not working in this place here. It is not working. Okay, so we can define somehow. We'll talk about this if you ask in the notes. Then we have this Cauchy theorem, which says that if gamma naught is integral or gamma 1, they are same. So, and the other thing is that when we again their integral same over gamma naught, and over gamma 1 they are same. So it is representation of gamma 1, then they are homotopic. So 2 is more powerful. So when representation, there we can use that part. So Cauchy theorem for second thing Sorry, I my device was disconnected. So is this now okay? You can see screen also. Okay, so we were talking about this Quasi theorems, these equivalence things. Either so yeah, so null homotopic over null homotopic curves, integral of holomorphic function is zero. Am I audible?
Yes, sir.
Okay, fine. So let we leave this. This example is good. So here fz is 1 by z on c minus 0. Uh, it is holomorphic, but if you see the problem of the function not being holomorphic is at 0, and this curve gamma t, which is e power it, which is circle, unit circle, integral is not vanishing. So either you see from the picture that the curve gamma, which is circle, unit circle, cannot be deformed to point. Yes, that curve is not null homotopic. So that is why integral is not vanishing here. Okay, because one origin is missing from C, and that circle, unit circle, is rotating once. Oh, maybe this is not good way to say. But integral is not vanishing just because that unit circle is not null homotopic. So this Gursa theorem, which is about for when Z1, Z2, Z3 are 3 points in omega, and omega is some open connected set, and f is holomorphic there, then uh, lines, segments, kind of polygonal path, the integral is 0. So if you prove for this, then we have for any polygonal path, the integral will vanish because all over polygonal paths, integral can be taken as sum of triangles, means sum of this arc of triangles. We'll see next. We are not going to see the proof of this. I hope you understood the proof. See, here is the thing I was telling to you. If we have some bigger polygonal path, means bigger concatenation, more than 3 line segments, then we can make them. This is just as a corollary we can see. So here they are using induction, but I was thinking that what we can do here, we can separate them into various triangles, right? And calculate for each triangles, each of these arcs, we have 3 line segments, and using the theorem, Cauchy-Grosset theorem, all integral is 0. Sorry. And if you add them, various closed thing, these red lines get cancelled because of being minus. Right. So overall integral is 0 on bigger polygonal paths. So that's the proof of this. Right. After this, for general curves, after this polygonal path, we will, if you remember, kind of result in second fundamental theorem. Any over any curve, you can approximate that integral of curve by a polygonal path, right? So that is useful. We'll see later in the here. Right. Cauchy's theorem for convex domains. Our convex domain we have our closed curve they are zero. So this is I think clear because we are just going to use second fundamental theorem. Antiderivative exists because we can define antiderivative this way. If you remember, uh, capital F of W is equal to fixing some Z, uh, any path from Z not to W, F of Z, dz, any polygonal path because uh, this is well defined function. If you take different polygonal paths, you can, yeah. So just like let's say Z naught is here and W is here, and you are reaching some polygonal path this way. Another way is this. Then what you do, this is let's say gamma 1 and this is gamma 2. You take integral over gamma 1 minus gamma 2 of f of z, and using Cauchy-Gaussian theorem for by this polygonal thing, it becomes 0. And that it will imply that over gamma 1 of integral or over gamma 2, they are same, and hence you can define this way any poly. So here in place of this, you can write gamma, where gamma is any path from z naught to w, this way, polygonal path. So antiderivative exists, and hence uh, integral is just depending on terminal points. And because here we are taking closed curve, so end points are same, means initial and terminal points are same, and integral becomes 0. So Cauchy theorem, next part is Cauchy theorem. This is the Cauchy theorem for general curves, and it is a big proof, I think. So again, the thing is that we are going to, if they are homotopic, let's say first curve gamma naught and gamma 1 is homotopic, then taking various partitions of homotopy, we can have polygonal paths where all this overall Cij is here. If you see this idea, uh, integral is 0, and you if you add them, you get this polygonal, and so we can approximate by uh, polygonal paths. Every curve can be approximated by a polygonal path. So the integrals are kind of same. So as partition length goes to 0, so our gamma is again integral is 0. This is a big proof. We are leaving this simply connected paths. So the last thing is when gamma omega is simply connected. This means that any closed curve is null homotopic here. So over any closed curve, because it is null homotopic, integral becomes 0. This theorem. Okay, let's see now the some exercises which were given as assignments to us. So let's start from here. Uh, week 6, question number 1. We can copy from here. Right. Omega is closed disk of radius 4 centered at 0. So let's draw the picture and understand what is happening. This is radius 4, means 1, 2, 3, 4. Okay, so our domain is this right, closed disk. And gamma 1 is curve, which is constant curve, and it takes value 0. So the gamma 1 is the constant curve at 1. Gamma 2 is e power it, which is unit circle. So this is gamma 2 point. This point is gamma 1. Gamma 3 is unit circle, not, oh, of course, this is unit circle centered at 2, right? So this is gamma 3. Okay, now we know these curves from picture. Uh, Now we're coming to the question, what is this first part? Omega is convex set. So you agree with me, it is convex set? So this disk is uh, omega, closed disk. Is this convex? Am I audible or not?
Yes, sir.
Okay, so I am audible and I am asking you question. You agree with me if it is convex set omega? Okay, so you see here it is a disk given any 2 points. If we join by them by line segments, the whole line segments lies here, so it is a convex set. What about B part? Gamma 1 is homotopic to gamma 2 with fixed endpoints. So one thing is you have to verify gamma 1 endpoints of gamma 1 and gamma 2 are same, right? Which is 1. Gamma 1 and gamma 2 both are curves. So gamma 2 is a circle and gamma 1 is just the end point, the constant curve. So end point is are same. Are they homotopic here in this omega? Because if you remove 1 point from let's say origin is removed, then they are not homotopic. Just we have discussed that gamma 2 is not null homotopic. The integral of e power it is not 0. Right. End points are same. Now next, can we give some homotopy? Just because they are convex, we can give them a linear homotopy, right? We have a linear homotopy from gamma 2 to gamma 1. You just like pick any point and line joining this one, and you can deform like this. So everything goes to 1. Okay. So what is that homotopy? You can explicitly write something like H 0 1 across AB, or here their parameter interval are 0 to 2 pi, which I'm not going to say. AB is also fine, right? and he from here to omega such that h of s comma t is equal to 1 minus s time gamma 2 of t minus or plus s gamma 1 of t, something like this. This homotopy works, okay? Because at s is equal to 0, what you have is this gamma 2t, and s is equal to 1. At 1 is stage 1. Stage 1, you this part becomes 0 and you have gamma 1t, which is 1, right? So this way you can define the homotopy, and the second option is correct. What about third part? Gamma 1 is homotopic as closed curve to gamma 2 in omega. If they're homotopic as fixed endpoints, they're also homotopic as closed curve. Okay, so B implies C is obvious. Same homotopy will be homotopy as closed curve. Okay, but the other part is kind of non-trivial. Homotopic as closed curve may not be closed at fixed point because maybe they have different endpoints. Initial and terminal points are different. Then closed homotopy as closed curve may not be homotopy as fixed endpoints. So this part is obvious. This is non-trivial. Means may not need not be. Okay. So what about D part? Gamma 2 is homotopic with fixed endpoints to a reparameterization of gamma 3. So now I'm asking to you, uh, what do you think? Where is so they're talking about homotopy with fixed endpoints. So first of all, required condition is that two curves have same endpoints, right? So what is endpoint of gamma 2? It's 1. What is endpoints are of gamma 1? So gamma 3? They are different. Here are the endpoints. So for D, gamma 2 and any reparameterization of gamma 3 or gamma 3 have different endpoints. So we do not have any homotopy with fixed endpoints. So the first condition is required that they have same endpoints, and we have some continuous function from 0 cross 1 to cross AB to omega. So, but we don't have different and we don't have same endpoints. So this is wrong. You can also use some logic if you are able to understand what I'm telling. Okay, omega is simply connected. You agree with me because it is a convex set. Convex sets are simply connected. We can give linear homotopy to constants. Just like gamma 2 is homotopic to gamma 1 and gamma 1 is constant. So we can say the unit circle is null homotopy. So this way, any homotopy, any curve is homotopic to the point, means to the gamma 1 constant curve. We can give some linear homotopy in similar way. So it is simply connected. Any because any curve is homotopic to gamma 1. Similar homotopy can be given as in B, as here. So you understand this question? So we can go to the next part. So if you understand, at least you can tell me yes or no. Right. Now we are going to see next question. Second question. If gamma is triangular path Z1 to Z2, Z2 to Z3, Z3 to Z1, Z1, Z2, Z3 being 0, 3i minus 4, then we have to calculate this integral. Okay. So its integral can be separated into two parts if you remember. If you see e power, because e power z is what? Entire function, holomorphic everywhere, and we have triangular closed curve. So let me draw the where is our path 0 to 3i, 1 2 3 here, and 3i to minus 4, 1 2 3 4, minus 4 is here. So we can draw the, so this is our closed curve, which is arc of triangle, and we know Cauchy theorem. I into e power z over gamma dz. This is 0. From where? By Cauchy theorem. Cauchy-Goursat theorem, whatever. So Cauchy-Goursat theorem. So we only need to calculate what is integral of minus I e power, sorry, z bar dz of gamma. So this is what we need to calculate. We want this integral. What it is, we can calculate in over three different line segments, and it can be written as I integral over gamma 1 z bar, where this is gamma 1, this is gamma 2, and this is gamma 3, z bar dz plus gamma 2 z bar dz plus gamma 3 z bar dz. Now, after this, we can write what is gamma 1, gamma 2, and gamma 3. So, okay, because so with this representation, we'll see what is gamma. Gamma 1 is what? Gamma 1 of t is equal to 1 minus t of minus 4. Means when t is equal to 0, we are getting minus 4. And when t is equal to 1, we are getting 0. Sorry, when t is equal to 1, we are getting 0. So t into 0, which implies that this is 1 minus t minus 4, which is we cannot write, we can write it differently. 4t 4t minus 1. Right. What is gamma 2t? We can write this in the similar fashion. So 1 minus t, at 0 we are getting 0. So here we have to write 0 plus t into uh, 3i. So at end point is 3i. So we just get 3it. What is gamma 3? We can also write with parameterization interval 0 to 1. 1 minus t, initial point is 3i, so we have to write here, plus end point is minus 4, so we have to write here. So what we are getting here is this minus 4t plus 3 1 minus t into I. Okay, so now we have all these three curves. You are following me? So do you understand how I'm writing this gamma 1, gamma 2, gamma 3? Hello. Okay, I hope you understand this. Uh, let's see what is our integral from here to here, minus I as it is, and in place of gamma 1 we are going to write 0 to 1, uh, 4t minus 1. Okay, yes sir, fine. You are understanding with me. It is very good. 4t minus 1 dt plus gamma 2 we are going to write 0 to 1, but so z bar, so we are going to put gamma 2 in place of z bar. Why I'm not writing bar here? Because 4t minus 1 is just a real thing. There is no imaginary part. That is why. So we just put 4t minus 1 into gamma prime t. If you remember, when we put f of z dz for gamma, it is a to b f of gamma t into gamma prime t dt. So this gamma prime t we are not writing, so there will be some error. So we are going to modify our errors. 4t minus 1 into 4 dt plus 3it. So we are going to write minus 3it because we are looking at z bar. Minus 3it. And what is gamma 2 prime, which is 3i dt plus 0 to 1 gamma 4, gamma 3 uh, minus 4t, and we have to take bar, so that's why I'm going to write it plus 3t minus 1 into I. Now after this we have to take gamma 3 prime, which is minus 4 uh, minus 3i dt. Okay, fine. Now we can solve these integrals. These are very easy now. In the last time we had some error in integral, so this time we are going to solve it carefully. So we have in the first place 4 square, which is, let me write outside, 0 to 1, and t minus 1. So we can directly write here t minus 1 whole square by 2. there is still error, right? So yeah, t square by 2 we can write in first place, and then t t square 2 is integral for t, and for minus 1 we will have just minus t. Integral is from 0 to 1, so we can write this plus. Now here we have 3 into 3, 9, I into I minus 1. So minus 1 get cancelled. We have just 9 outside. Inside we have t. So that t becomes t square by 2. And integral is from 0 to 1. Plus, now this part. So, okay, we can solve it further. Minus 4 minus 3i is outside because it is constant. Minus 4t becomes minus 4t. Okay. So inside we have minus 4t square by 2 plus 3t, which becomes plus 3t square by 2. Minus 1 becomes t, and I as it is 0 to 1 this integral. Now we can solve it, right? How? Minus I here. Inside we have 16 into t square. When t is equal to 0, this is 0. When t is equal to 1, this is minus 1 by 2 plus 9. At 1 it is 1 by 2, so no problem. 9 by 2 uh, minus 4 minus 3i, or 4 plus 3i, we can take minus outside. Now at t is equal to 0 we are getting 0, t is equal to 1 we are getting 4 by 2. So we write in bracket minus 4 by 2 plus 3 by 2 minus 3i. Okay, so further minus I here, we get minus 8 plus 9 by 2 minus 4 plus 3i, and this can be solved. 3 by 2 minus 3 by 2 minus 3 by 2, and this is minus 2 minus 3 by 2 I. So now we can solve it, but I don't want to solve this because this is okay. If there is error, we don't get an integer solution. Otherwise, we should get some integer solution. So with this hope, let's solve it happily. Okay, minus from outside the bracket, it becomes plus, and 8 into 2 minus I outside. 16 minus 9, which is 7 by 2 minus 7 by 2, and plus 4 into 2 becomes 8. 3 into 3 by 2 becomes 9 by 2. With I and I multiply together, minus 9. Now 4 into 3 by 2 becomes 6 plus 6i, and 3 into 2 becomes 6i again. So these three things, 9 into 7 get becomes 0, and you just get minus I outside, 12i inside. This becomes, when minus I is multiplied inside, it becomes 12, right? This is our solution. Okay, you also solve this calculation, verify. if there is any mistake, but I hope there is no mistake. Okay, so now we can go to next question. You understand this? Fine. So here we have gamma closed curve, which is circle of radius pi by 4 and integral of tan z by 4. So what do you know about tan z? Is this holomorphic kind of entire function or not? You can unmute and tell me. Tan function, is this an entire function? Hello. So it may not be entire, but okay. For example, if you see at uh, pi by 2, what it becomes? At pi by 2, tan pi by 2 is infinity, which is not well defined number, means not a complex number ring, right? So it is not well defined at pi by 2. So the problem is at pi by 2. So in this small domain, the open set, which is not containing pi by 2, so it looks like coronavirus. Sorry. So a small open set which contains the circle, which is not containing the pi by 2 thing, means where it is not defined. So other thing there is here it is holomorphic. So we can, what we can do, so we know that that tan is not entire function, or tan function is not well defined at uh, defined at multiples of pi by 2, means n pi by 2, where n is belonging to z. Why I'm writing this is just because, if you know, casting becomes 0, because tan z is equal to sin z by cos z, and cos z becomes 0 when z is equal to n pi by 2. Is this fine? We can choose omega is small enough omega a disk of radius, let's say bigger than pi by 4 but lesser than pi by 2, something like this. sorry, omega is small enough disk such that tan is holomorphic uh, holomorphic on omega, then we can use Cauchy theorem. General for Cauchy theorem for general curves. Here it is Cauchy theorem for closed curves maybe, because disk is also omega is convex set we have chosen disk. So Cauchy theorem says integral over gamma of tan z is equal to 0. Okay, do you understand this? What I did? Hello, you can give some response so that we can go ahead. Yes, okay, fine. We'll see next question, but uh, let's introduce ourselves so that you don't feel shy. So, who am I? I am a PhD student at Aisa Mohali. My name is Aman Singh, and currently I'm in third year. No, not in third year. Yeah, fourth year started just now. My hometown is Prayagraj, and I did my MSc from Kerala School of Mathematics. So, what do you do? You also introduce yourself. Hello,
Yes, sir.
Emma.
Can you repeat me? Yeah.
So you introduce yourself. I just want to hear.
Oh, yes, I am Hemalata. Currently, I'm living in Bangalore, but my native is Tamil Nadu.
Hmm.
Yeah, I'm
You
PG
do
with B.Ed. Yeah, I'm PG with B.Ed and DTL.
okay.
Yeah, I'm doing this NPTEL for my working profession. I'm
Okay, okay,
basically a mathematical teacher.
fine. Okay, so you are understanding what we are discussing, right?
Yes, yes.
Okay, fine. So let's continue with our discussion. Okay, so now coming to next question. Fourth, the fourth question is about truth and false. So we are given two statements, and we have to see if they're true or false. So the first question is gamma 1 is given a curve of which is closed curve, which is circle of radius 4 centered at origin. Let's draw the picture and things will be clear. Of 4 radius, we have a circle, and gamma 2 be a polygonal path where this is 2i to my okay from 2 to 2i this way, and 2i to minus 2 2 to 2i, sorry, 2i is not here. 2i is here somewhere. 2i minus 2i is, so minus 2 is here, minus 2i is here, right? So we have this polygonal path, right? It is not drawn very well, because if drawn very well it should have been a square, and it doesn't look like a square, but you assume that it is a square. Okay. uh, we have to see that integral of these over these two curves, they agree, yes, they are same. So first of all, is function holomorphic? Is function entire? Not entire. Where is the problem? Problem is that when z square plus 1 is becoming 0, z square plus 1 becomes 0 exactly when z is equal to plus minus I. And where is the plus minus I? Plus minus I is here, here and here. So function is not holomorphic, and curve is not kind of uh, there is some situation. In the classroom we have understood then omega is convex head, and function is holomorphic, and from first curve and second curve, though they are represent reparameterization of each other, then integral is same. If they are homotopic to each other, then they are same. But here function is not holomorphic. But one thing is clear, that from one curve to the other curve we have a linear homotopy, right? Linear homotopy means there is no problem in here. Here in this area we don't have any problem. What we can do, we can just from here to here, we can from one curve to we can move to the other curve smoothly. Okay. So the main problem is at these 2 points, and these 2 points are not taking part in homotopy. So whatever homotopy we are going defining by these arrows, uh, we don't touch those points. We don't ever cross those points, right? So the good thing is that uh, we have homotopy from one curve to another curve drawn in the picture. So the picture is drawn, and I'm not going a linear homotopy. That is clear. Let me we have a linear homotopy from gamma 1 to gamma 2. So integrals are same. Okay. Integrals, they are not going to change. Integral over gamma 1 of f is equal to integral over gamma 2 of f. Even if function have singularity, we don't know. But if those two curves are homotopic, then we are fine. Integrals are same. Okay, there is no problem in calculation. They are non-zero. Of course, they are non-zero. They may be zero, but we cannot use Cauchy theorem to show that these two integrals are zero. But if whatever the integral over first curve is, the same integral is over second curve, because they are homotopic to each other. So the first option is true. Okay. Now coming to second, we have a rational function, and this rational function is not holomorphic at where. So z square divided by z square plus 5z plus 6 is not holomorphic where? Holomorphic at z such that z square plus 5z plus 6 is equal to 0, which means z is equal to plus, sorry, minus 3 minus 2. So we draw the picture, and we are going to take integral over gamma. Gamma is unit circle. This doesn't look like unit circle, but the geometry, this is minus and this is minus, plus minus. Over this curve, we are going to take integral. Where is the minus 2 lies? Minus 2 is here. Where is minus 3? Minus 3 is somewhere here. So we can take omega, this, this is our omega. So omega is disk with same center with radius maybe 3/2, center 0. So in this omega, so in omega, choose inappropriately. F is holomorphic. F is holomorphic, and we have chosen that this is convex also, simply connected also. We can use our Cauchy theorem. Using Cauchy theorem, we get integral 0. Integral of f over gamma dz is equal to 0. So this second part is also true. So I hope you understand them. So we can see next question. So this next question is our last question. After this, what we can do is, uh, if you have some doubt, you can ask. Otherwise, we'll leave. Okay. So this question is done in our problem session, if you remember. But we'll see this time again the same question, and that will require where we can use complex analysis to solve them easily. This is an infinite integral. So how can we write it this way? This integral, let's say this is I, is can be written as limit r tend to infinity, leave this constant, or maybe root pi by 2 this other side, root pi by 2 this side. Limit r tends to infinity, integral from minus r to r sine of t square dt. No, in the classroom, this was not similar question. Sorry, my fault. There was from 0 to r, it was given. 0 to infinity, the integral was calculated from 0 to infinity. Now here we have minus infinity to plus infinity. But if you see what is this function, is this even function? If you put value t in plus or minus, they're symmetric kind of. When you put plus 5 or minus 5, you get same value. So this function is even. So what we can write to this function? This further can be written 2 into limit r tend to infinity minus r to plus r. Now not from minus r. This becomes from 0 to r. Okay. Sine t square dt. Fine. Now everything is clear. So this value has been calculated in the classroom, but we'll calculate this and because we have time, we can calculate once more so that you understand this well. So for this, what we can do, a similar function e power z square. If you write e power z square and you take this closed curve, let's say this is capital R, 0 to capital R. This is our where we want to calculate. But what we are doing here, we are making a pi by 4 angle and the circle. This is R e power it. Now this function e power z square is an entire function. So if we have an entire function and we have a closed curve or concatenation of curves which is closed, then integral of this becomes 0. So integral, if you calculate integral over this, let's say it is gamma 1, this is gamma 2, this is gamma 3, and as arrow is defined there. So integral over gamma 1 of whatever f is fz dz is same as integral over f is entire, that is we are already noted, gamma 2 minus gamma 3. So here we have null homotopy, but gamma 1 is equal to gamma 3 minus gamma 2, this one. So we have gamma, these two are homotopy. So gamma 3 minus gamma 2 fzdz. Now we are going to calculate. So the left, what is left part? Left part is so how are we going to get sine t square? We are not getting sine t square. So what if we put multiplied with I, e power I z square? So the left side becomes 0 to R. Fz is e power I. Z we can replace by t because it is now real. T square dt. And you see here, when we calculate the integral, it becomes cos t square plus I sin t square. So the imaginary part of this we are going to focus. So what will be our answer? Our answer, this will be, let's say this is what we want to calculate. This is, let's say, capital T, or not T. We can use some other thing in S. So S will be imaginary part of this. Imaginary part of this. So we first calculate and then we'll focus on imaginary part. So this is equal to, not this, RHS of star. It's equal to gamma 3 minus gamma 2 of fz dz. Now in place of gamma 3, what we have? Gamma 3 is this line, which is gamma 3 of t is equal to zero to r. So we can t e power I pi by 4. T running from 0 to r. So we can reparameterize it, make it interval 0 to 1, but no problem. So at the end, we'll put r is equal to infinity or r tends to infinity. So no problem to that. So what is gamma 2 of t? Gamma 2 of t is r e power it, where t is running from 0 to pi by 4. Fine. Now we are going to come. We are going to write our things explicitly. Okay, gamma in place of gamma 3, we are going to write e power. This is for gamma 3. Gamma 3 is reparameterized from 0 to r, so we can write 0 to r e power I t square. T in place of t square, we are going to write gamma t square. Gamma 3 is t plus e power I pi by 4 square into gamma 3 prime, which is e power I pi by 4 dt. The next part is over gamma 2, but we are going to write minus gamma 2. So minus gamma 2, we are going to replace our limits, or we can just write minus outside. So that is also minus comes outside. If you minus of now gamma t from 0 to pi by 4, we have e power I t square. So we are going to write gamma 2 square, which is r e power I t 4 square into gamma 2 prime, which is r e power I t again dt. Now we can calculate further. Uh, so e power I pi by 4 is 1 plus 1 by root 2, because sine pi by 4 plus cos, sorry, plus I cos pi by, which is again 1 by root 2. So 1 plus I by root 2. And 0 to r as it is, e power I t square, we can solve it further. So it becomes e power I pi by 4 is some constant cos this is a constant. So what we can do? E power I into that constant. So we can write that. I think so. The answer is clear from this step. If you use from the classroom, we have calculated this is something root pi by 2, root pi by root 2 by root 2. This integral is uh, root pi by 2 root 2. Okay, so if you want to calculate the answer, this is fine. This whole thing, now if you put this equation, I will be equal to 1. So this answer is 1, but we are going to calculate this integral. Okay, again. So what can be done now? 1 plus I by root 2 e power I t square. Why sad? Very sad. So why plus here? What is this plus doing here? So there is some mistakes. You could also pointed me out. So when we are writing gamma 3, we are not, it is just t into e power I pi by 4. Now it is fine. Now what is e power I pi by 4? It's just 1 plus I by root 2. So when it is Sorry, I have to leave now. Okay, you can leave. Uh, you know how this is solved. I will record maybe or finish it here. Thank you for joining. Okay, so now no student is here. We can solve or we can leave it as it is because this is done in the classroom. Okay, so we are leaving now here. Let me delete this part because we are just using something which is done in the classroom. So no need to write once more. This living at this place, uh, cal- limit r tends to infinity 0 to r sine t square dt. Uh, this was root pi by 2 root 2 uh, already calculated in problem session. Okay, so that's then. So we get this value 1. Okay, so we'll see next week.